part 2 of lecture 6. So in the previous part, we talked about how to train a decision tree. And at the end, I didn't talk about pruning. So now I want to talk about it. And before that, let's recap what happened with training a tree with a diagram. So suppose we start with a large training set like this, and we figure out the most informative features, say like x1, and then we split the data set into two parts. The first part is all the data points with feature 1 being 0, and the second part is feature 1 being 1. So we have these two smaller data sets. And then we repeat the same process. So here, suppose x2 is the most informative feature, and then we can split, say, this way, and we have this half and this half, and we can split again, say like in the middle, and then we can have two smaller sets. So now suppose all the labels here are 0, they all belong to class 0. Then we're going to create a leaf, and the leaf would have label 0, and here suppose it's 1, it's okay. So suppose we can stop here as well, and let's say create another one. Let's say split by x4, and maybe you want to split again here. Let's say the first set is a bit smaller, and the second set is large. So say this is 0, this is 1, let's say this is 0. So we create a tree this way by just splitting the data set and find the most informative feature. So now there's a problem. We are stopping until we get to a very, very small training set with the label being the same. So if we start with a very large training set, it means it takes very long, so the tree will be huge, right? So what it means, we'll get a large tree. The problem is we don't like large trees because they are hard for us to make decisions based on like a huge tree with 100 levels. But that's not the important problem, actually. The important problem is overfitting. So remember we talked about overfitting before. Overfitting basically means it fits the training set so well that it does not perform well on the test set. And this is actually a problem here because we stop until everything is basically classified correctly in the training set, right? Because we are stopping until everything has the same label. So in particular, everything will be classified correctly. So that for sure will overfit the training set. So remember we talked about regularization. So we're going to do regularization again here. So the lambda stuff will probably not work here because we never want to use lambda. So another technique seems to be useful called the validation set. So what we'll do at the beginning is from the training set, we will take out a part of the training set as the validation set at the beginning. So we only train the decision tree based on the remaining training set. So we just set this apart. And then we train the complete large tree. And then what we'll do is we will cut some of the branches. But by the way, the word pruning just means cut branches of a tree. And also in English, it is pruning also means cutting branches of a real tree. So the only difference is here, pruning, when we cut off a branch like this, we need to add back a leaf. And in real life, I don't think we need to add back the leaves. So I guess that's the only difference. And now the problem is, when do we cut the branch and what leaf do I add? Right, so let's talk about the first problem. So if we compare the accuracy on the training set of whether to cut or not cut the branch, of course we're going to not cut the branch, because having the branch would improve the accuracy on the training set for sure. So what we're going to cut is when the accuracy of the validation set is not decreasing. Yes, not decrease. So basically what we're going to do is we compute the accuracy on the validation set, again, not on the training set. We compute the validation set accuracy with this subtree and without this subtree, and see which one is larger. So if with the subtree is larger, we'll keep this subtree. And if not, if they are the same or somehow magically increases, then we will just prune the tree. So that will be the first important point. And second, how to decide what leaf do I add? Because some of these are labeled 0, some of these are labeled 1. So what we're going to do is we're going to use the majority class of the training set, not the validation set. So here, suppose there are more 1s than 0s, we're going to create a leaf that labels this leaf 1. So these are the two important things, and they are summarized in the next slide. Basically, let me repeat this. When we figure out the label of the leaf, of the new leaf that we, after we cut the subtree, we use the majority of the training example. And when we are comparing whether we should cut the tree or not, then we compare the accuracy on the validation set. So we are using different sets to create and cut the tree. And of course, for the whole tree, we need to see whether I should cut this subtree, whether I should cut this subtree, and so on. Basically, we need to try all of them. So it's a lot of work, but the algorithm is basically the same for all subtrees. And this is actually one of the simplest ways to prune a decision tree. It's called reduced arrow pruning. So you can use this for P2, or if you can find some more sophisticated way to prune a tree, you can try them in P2 as well. So next, I want to talk about something different. Basically, I mentioned at the beginning that we're going to combine lots and lots of trees to make a forest, and this is what bagging is doing. So suppose we have a large training set, and then we can create like one tree, and then we can create another tree, and then we can create another tree. They look like broccoli, but suppose they are trees. In any case, suppose we're using the same training set, then it seems these trees will be exactly the same, because there's nothing random with the decision tree algorithm, right? So we're not picking random features to split. We're always splitting according to the most informative feature. So these trees will actually be exactly the same. And even if we are using different validation set, they will be like very similar. So we do not want to use the same training set. So what we are going to do is some process called bootstrapping. And what that does is basically sampling with replacement from this training set. So what we're going to do is we sample something here with replacement, basically a smaller set. If it's small enough, we create the first tree based on this, and then we sample again, create a second tree, maybe sample again, create another tree. Then these three will be based on different training examples. They will look different if the smaller training sets are small enough. And that's what we're going to do. We're going to use small subsets to train different trees. And at the end, I will just ask all of these trees to vote. Like we get a new instance, we use the first tree to predict, say it predicts 0, second tree predicts 0, so tree predicts 1, then I'm going to take the majority. So I'm going to classify the new instance by 0. So that's basically all about bagging. And for these simple procedures, we always need a fancy name. So we are going to call it bootstrap aggregating. And we also always need a shorter version. So we are going to take random number of characters from the beginning of each word, and then it becomes like bagging. So bagging has nothing to do with bags, and it's just bootstrap aggregating. So aggregating is just how you like combine these trees, and bootstrapping is a technique from statistics, and it's the basic idea is, suppose I fall into the water, how do I pull myself up? So suppose I'm wearing a boot, and I can pull on this bootstrap, and hopefully if I keep pulling my bootstrap, I can pull myself out of water for some reason that I don't understand. But in any case, this technique just says, suppose we have a very small training set that's not enough. How can we help ourselves up by just creating new training data? And the answer is just sampling with replacement. Then we get basically more samples, and then hopefully we can help ourselves. So that's the idea. And if we combine bagging of the training set and also bagging of the features, basically we are using random subsets of training set and also random subsets of features to create those trees, and also we do not prune those trees, then the algorithm will be called random forest. So if a single tree is not good, then a random forest, in theory, will be able to have any kind of decision boundary, just like a neural network. So I will actually show you a demo here. So here, the link is on my website, week 2. And so here, suppose we have 100 trees. That's the number of trees. And we can also limit the maximum depths of each tree. And the hypothesis, the number of hypotheses per node is basically how many features do I sample from the whole list of features. And we can change the number if we use more trees. Well, maybe it's better, maybe it's not better. We can add more points, and we can also change these. So you can play around with this, and then you can see that the classification boundary can be kind of arbitrary, just like in neural network and in kernel SVMs. Okay, so let's get back. And the last improvement of decision trees is called boosting. So the idea of boosting, actually similar to bagging, is we're going to use lots of decision trees, and hopefully if we combine them, we can get a better classifier. The difference is that we're training them sequentially. So we will train the first tree, and then the first tree will be making mistakes on some of the instances. Then we will train the second tree to focus on fixing those mistakes made by the first tree. And then we'll train the third tree to fix the mistakes made by the first two trees. So if we do this repeatedly, then hopefully we can get a forest that's kind of focusing on different parts of the instances. Focusing on different parts of the training set. So that would be the basic logic. And maybe let's look at some of the specific mathematics. So one thing I forgot to say is that boosting is not a combination of two words. One word starting with boo and the other one ends with sting. It's just one single word called boosting. And one specific algorithm with this boosting idea is called adaptive boosting. And now we have a shorter form called a.boost, and it goes like this. So first, we need to assign weights for each instance. Note that these are not weights for the trees, they are weights for the instances, and they measure how difficult each instance is. How difficult is it to classify instance I, say xi? So at the beginning, we are going to assume they are equally difficult or equally easy to classify. And after each iteration, we are going to use these weights and train a new decision tree. And decision tree number k will be focused on minimize the weighted mistakes, and the weight is how difficult the instances are. So what we're going to do, that part is basically the weighted number of mistakes. And the weights are basically the difficulty. And we're going to find a tree that basically focus on fixing the problems with the harder to classify instances, and we will call the number of mistakes epsilon k. And based on the value of epsilon k, we will say whether the tree is good or not. So we call it another set of weights. These are the weights for the tree now. So these weights, alphas, they are how good the tree is. And they are based on the number of mistakes this tree is making. And then every time we need to update the difficulty of the instances. So we are going to update it using a formula like this. And maybe let's look at this more carefully. So there are two cases. One is if fk classifies things correctly, classifies this xi correctly. So what we want is we want to decrease the difficulty. So we want to decrease the weight. Is it true? If it's classified correctly, it means they are equal. The classification and the actual label, they are equal. So this number will be 1. 2 times 1 minus 1 is 1. And this is e to the minus alpha k. So this will decrease the weight, which is what we want. And if it classifies xi incorrectly, then hopefully we are going to increase the difficulty because it's classifying it incorrectly, so it's difficult to classify. And here, this indicator will be 0. 2 times 0 minus 1 will be minus 1, and the minus cancel out will be just e to the power alpha k. And we're using this to multiply this, and it's going to increase the weights. So basically, it's what we want. So we update the weights that way. So there are different versions of this formula, but the general idea is the same. So for a correctly classified instance, we will decrease the weights, otherwise we'll increase the weight. And now, at the end, if we get a new instance, how do we classify? Of course, we're going to let them vote again, but we have weights now. So you can think of the weights as number of votes each tree gets. So basically, the first tree can vote like alpha 1 times, and the second tree can vote alpha 2 times, and the last tree can vote for like alpha k times. And then after they all voted, we use the weighted majority as the label of the new instance. So there is a special case where there are only 2 classes and alpha is normalized so that everything sums up to 1, then we can use a simpler formula. So the way to understand this formula is if, say a lot of the more important trees, a lot of the better trees are voting 1, then that sum will be large, so it will be larger than 0.5. So we will classify the new instance as 1. And if a lot of the trees, especially the important ones, are voting 0, then the sum will be small. So in particular, it will be smaller than a half. So we will classify the new instance as 0. So that's the idea.